Okay.
Okay, so our next speaker is Scott Evans, and he will be talking about the entropy economy and the Kolmogorov learning cycle. Yeah, thank you.
Thanks, Benjamin. And yes, my name is Scott Evans. I'm at G Research and also an adjunct at the University of Albany. And I'm very excited to present our concept for the entropy economy and how it relates to what we're calling the Kolmogorov learning cycle. You can find information about our project here at this website that's listed, and feel free to email me with additional questions or other opportunities. But basically what we're trying to address is that by 2030, by some estimates, up to 20% of all energy used in the world will be used for compute technologies, either at HPCs or other compute, which could amount to a significant amount of carbon. And so to address that, we were looking at basically our thesis is that the fundamental unit that we should be looking at to optimize to deal with carbon and compute is entropy as opposed to energy. And so we have this idea of the entropy economy, and what I'm going to be talking about is how we can optimize jointly compute and learning through what we call the Kolmogorov learning cycle. This could be used to not only reduce carbon, but also stabilize the grid and make additional use of renewables. And so a couple of quotes to kind of start out with. So the great David McKay, Oxford professor, whose textbook I use for machine learning, speaks to, kind of one of the theses of this conference, of this symposium, is, why unify information theory and machine learning. And his view is that they're two sides of the same coin. Even more so, I think, algorithmic information theory, because it's dealing with fundamental data objects as opposed to, assumed models. But also, he said this in his book on sustainable energy without the hot air. He was saying, shouldn't we really be optimizing energy? Energy is neither created nor destroyed. And he said, it's really about entropy, a trickier thing to explain. And he talks about how, we move entropy from high to low and get different quality. And, he says in his typical, kind of snarky way, it's convenient but sloppy shorthand to talk about the energy rather than the entropy. But the right thing to do is to really bring it back to entropy. And he's just talking about optimizing it in the thermodynamic sense in that case. When we bring in the information theoretic sense, I think we can really get to the total optimization. And here's what I was talking about in terms of the the energy use. There's wide error bounds around this, and it has to do with how much efficiency is going to get improve as we expand AI and machine learning. But still, lots of carbon is going to be produced, and we need to figure out how to optimize that. So basically, what we're saying is we want to optimize both thermodynamic entropy and information theoretic entropy at the same time, so that we can basically understand how can we learn as much as we can, because compression is learning, as many people have asserted in this conference, and the compression bound is the information theoretic entropy. It's how we decide how well we're doing in a lot of these machine learning algorithms, and many people have been talking about maximum entropy equations and things like that. But so we want to learn as much as we can by as measured by entropy, but also lose as little entropy as we can out of the system as waste heat. So basically, if we're jointly optimizing compute and learning, then we're optimizing the entropy economy. And I take it back to the Kolmogorov structure function. And there's been a couple of talks that have addressed this. The Kolmogorov structure function, illustrated by Kolmogorov and Peter Gax is the presentation that I really like, where basically separates the Kolmogorov complexity into two parts. The one part that basically defines the set to which your data belongs, and then the second part enumerating that set and picking out the data from within that set. So for example, if you had a 128-bit string of alternating ones and zeros, right? Shannon entropy would tell us that, hey, that's possible. You could flip a coin 128 times and get that string. It could be a member of the set of all 128-bit strings. But we think that there's something special about that string. So we could add model to that. We could basically constrain that set by our description and say, okay, it's actually the member of 128-bit strings with equal numbers of ones and zeros. So now we have this typical set with, equal entropy that we can, enumerate with fewer bits, right? So our model cost has increased, our data cost has reduced. And we might even continue along that line to, find a set of just 2 elements of 128-bit strings with alternating ones and zeros. So now we've got a longer Kolmogorov minimum sufficient statistic and a smaller set of just 2 elements to which it might belong. So basically traversing this curve here, right? And Peter Gax defines the Kolmogorov minimum sufficient statistic as this K star here that is the optimal point. So this would be the sophistication length is the first part, and then the unsophisticated part of the data is the second part, the random part. So all the regularity is found in the first part. And I equate this to the variance bias trade that we've been talking about in this conference a lot. So I think that the seek to find the quest to find the optimal bias variance trade in machine learning equates to finding the Kolmogorov minimum sufficient statistic, which basically finds as much regularity as you can in the data, but also generalizes the best. So if we take that, here's another simple example that we used in this reference where we were looking at microRNA and finding simple sequences. We've developed an algorithm we called MDL compress that basically looks at the set of the smallest grammar problem and finds a dictionary that does the most of compression in it, and thereby finds meaningful phrases in the data. So for example, if you had this phrase, a rose is a rose is a rose, a longest match algorithm would maybe take half of it and put it in the dictionary, but that would lose maybe some of the sub structure that is important, right? So if we run our algorithm, we get this, this set where, our first variable equates to this object, a rose. The second variable combines that, is a rose, and then the total string is breaking down into just 3 variables, right? And from that, we can create a typical set to which other equally likely musings might belong of this poet, right? That balances that bias variance trade and finds these meaningful phrases that, we could look at. And actually, we were able to investigate this on microRNA and find motifs related to cancer by, pulling out the meaningful phrases within the DNA sequence. But along the way, we're doing that. We're expending effort, we're expending work, we're expending energy. And so what we've added to the Kolmogorov structure function is what we call this basically Kolmogorov learning function, which basically deals with the energy cost in doing the search for that minimum size program, right? And so when we start with no program, we haven't expended any energy. And then as we look and search for additional, gain in creating our Kolmogorov minimum sufficient statistic, we expend energy. If we expend, search beyond finding K star, we're basically just wasting energy, right? And so we certainly don't want to do that, but we may even want to stop early, right? If we can pull up early with a model that provides the quality that we need, we can also save energy, save carbon, right? So basically, this is our learning structure function that basically maps on top of the Kolmogorov structure function the energy profile along with the learning profile. And so we want to basically get to the best model that we can with the least amount of energy, the least amount of carbon. And beyond that, what we're looking to produce is a cycle similar to the great thermodynamic cycles that are used throughout thermodynamics, the Carnot heat engine, the Rankine cycle, things like that, where entropy is used to basically define the max efficiency that you can get in your cycle. All right, so what it might look like for the Kolmogorov learning cycle would be, you start with input data and you are looking to compress that data, right? So you expend energy to find the best model, the maximum compression of that data set, right? And so work is expended, temperatures increased, entropy is reduced as you sort this input data into something smaller where you can have a bunch of blanks, right? And Charles Bennett and others, told us that anytime you erase a bit, basically you release this amount of energy into the atmosphere, the Boltzmann constant times the temperature times the log of 2. joules are released every time we release these bits. So if we do our learning work to figure out our model, when we finally erase the stuff we don't need anymore, our temperature is going to increase. And now, and also the entropy is going to increase, because now we're going to have this smaller set that is, less redundant, right? Because it's gotten rid of the redundancies through the learning. And then from there, the cycle continues. Wolpert and others at the Santa Fe Institute have coined the term Kolmogorov work, which is basically the amount of energy it takes to run a program of size Kolmogorov complexity on a Turing machine to produce its output, right? So once we've learned our model, we execute that model on a universal computer. The amount of energy spent then is reflected here. So similar to like a Carnot engine, we're seeking to have a Kolmogorov learning cycle, and similar to the ways that entropy is used as a bound on the efficiency of that engine, we want to start being able to talk about the efficiency of our learning work cycle, and that will be, to the end of trying to reduce carbon and do maximum learning for minimum waste. So you could apply this type of principle in kind of a simplistic sense by having a data center, say, at a wind farm. So tragically, sometimes wind farms curtail energy because the grid can't take all the energy they produce. So they just freewheel spin and take less energy than they can. So if we were able to move the information work jobs to where the energy is, we would be taking the entropy out of the air and turning that into useful work, and eliminating the need to have a carbon credit, because we've eliminated the need to pollute at all, right, by doing this information work locally where the energy is. You can take that and move it into a grid type of structure and have like this kind of think of it as like a shock absorber for the grid, located at every renewables plant, any kind of power generation plant, right? So that we can move the information work to jobs to where the clean energy is, and in the same way, along the way, stabilizing the grid. But even within each high performance compute center, what we'd like to do is optimize and create energy aware machine learning algorithms that can make the trade between how much energy it's consumed, what the quality of output is, and what the throughput is. So, we talked about the equation for how many joules is released every time you erase a bit, right? If you use fewer bits, you'll erase fewer bits, right? So just getting the right bit quantization, right? Do we really need 64-bit quantization of every time series that we're analyzing? And if not, how do we create architectures to harvest the benefits of using less? Some exist already. Some would need to be created to take advantage of this. But theoretically, at least, if we use fewer bits, we erase fewer bits, and we produce less carbon, and that may have minimal, if any, effect on the quality of the model's output. Other parameters like the number of trees and bootstraps and threads and Bayesian optimization that we use in creating our algorithms can help us, make this energy to quality trade, dimensionality reduction, learning rate, things like that. So after we have these algorithms where you can kind of turn these knobs, then we would like to be able to adapt our training to a given energy profile. So you could have the opportunity to create only green models, just adjust your algorithm as the wind energy changes at the site, as the solar energy changes at the site. And then once we can adapt to a given energy profile, we can then prescribe a given energy profile from our information work jobs. And in that way, stabilize the grid, move power around, respond to casualties on the grid, and ultimately reduce carbon. A simple experiment we did, this is published in a paper we did at the Asilomar conference last year. My colleague Tapan Shah did analysis of just a simple learning algorithm using coefficients of order 14 bits down to 2 bits. Right, and what he found is for 2 bits, yes, the performance suffered, the learning error was greater, but even just 4 bits, gave almost the same performance as 14 bits, right? So if you reduce again, fewer bits erased, fewer bits erased is less carbon for almost the same quality. So I'd like to acknowledge my colleague Stepan Shah, who produced that graph, as well as my colleague Aklas Pandey, another co-author on this paper. Please check out our page here on the entropy economy and contact us. And we'd love to hear more about how we could partner and do more to do this joint optimization between learning and power, compute and thermodynamics, so that we can move from a world where we're producing so much carbon to a world where we're leveraging every renewable that we can and learning as much as we can. Thanks.